In this second lecture, we will discuss the structure of camphoric acid. Camphoric acid. In the previous lecture, we have seen that this camphoric acid is obtained after oxidative degradation of camphor. The molecular formula of this acid is C10H16O4. This compound is saturated dicarboxylic acid. Dicarboxylic acid. Saturated dicarboxylic acid. On heating, the compound will not release carbon dioxide, indicating that both carboxylic groups are on different carbon, are not on same carbon. This compound can be easily converted into monoester, but the formation of diester is very difficult. That is C10H16O4. When allowed to react with alcohol in the presence of conc H2SO4, it is converted into monoester easily, but the conversion of the compound into diester is difficult. This esterification indicates that one carboxylic group is attached with 3° carbon, that is carboxylic group is tertiary, and the second carboxylic group, which is esterified easily, is either 1°, that is present on 1° carbon, or present on 2° carbon. So in this dicarboxylic acid, we have two carboxylic groups. As the compound on heating is unable to release carbon dioxide, which indicates that both COOH groups are on different carbon. as it is known that esterification is the characteristics of carboxylic acids. So when this dicarboxylic acid is esterified, it is easily converted into monoester, and the formation of diester is difficult. It is known that due to crowding at 3° carbon, the formation of ester by 3° carboxylic acid is very difficult, and hence we can say that one carboxylic group in this dicarboxylic acid is 3° and the second carboxylic group is either 1° or 2°. This compound, that is camphoric acid, when brominated in the presence of phosphorus, red phosphorus, HV reaction, it is converted into monobromo derivative, it is unable to give di or tri-bromo derivative. This HV reaction is the characteristics of carboxylic acids having one or more alpha hydrogen. When this type of structure is present in the molecule on bromination, it will provide us when one alpha hydrogen is present, monobromo derivative is obtained. When two alpha hydrogens are present, dibromo derivatives will be obtained. And the formation of monobromo derivative indicates that the easily esterified carboxylic group is essentially 2°, it is not 1°. So, this compound having one carboxylic group attached with 3° carbon and the second carboxylic group is attached with 2° carbon, 2°, 3°. This compound C10H16O4 when decarboxylated, completely decarboxylated, it will give us cyclopentane derivative. Cyclopentane derivative. So we can say that this camphoric acid having one cyclopropane unit. So it is a monocyclic compound. and the presence of monocyclic ring is also imagined by calculating index of hydrogen deficiency. The index of hydrogen deficiency for the compound is 3, in which 2 ISD are due to two carboxylic group, and as the compound is saturated, there is no carbon-carbon double bond or carbon-carbon triple bond, so we can say that the third IHD must be satisfied by monocyclic ring. Monocyclic ring. So this camphoric acid is cyclopentane derivative having 2 carboxylic groups. This compound is (1,1,2) trimethyl cyclopentane. Suppose this is the basic unit for the molecule X. This unit is obtained after the removal of carbon dioxide, so carboxylic group is essentially present on any position of the ring. If we try to adjust the carboxylic group in this ring, one carboxylic group is essentially present here because it will represent 3-degree carboxylic acid. And the second carboxylic group, which is secondary, may either be present here or here or here. It may have 3 positions. Where is the actual position of second carboxylic group? We will get information by this reduction. When this compound is reduced with concentrated HI, it is converted into pentamethyl. Pentamethyl cyclopentane. In this framework, 2 additional methyl residue has appeared. It is known that when a carboxylic group is allowed to react with HI red phosphorus, it is first converted into acid iodide, then aldehyde, then primary alcohol, and finally it is reduced into methyl unit. So carboxylic group by this reduction process is converted into methyl residue. So 2 additional methyl residues in this product, in this reduction product, are due to the carboxylic group. And hence, we can say that our second carboxylic group is present at this position. Then this one. So this compound is our camphoric acid. This compound is camphoric acid. We can write different structure for the compound. This is camphoric acid. Camphoric acid, and this acid having 1 gem dimethyl unit. So we can write it. This is equivalent to this is camphoric acid. And this is our isocamphoric acid. This camphoric acid when allowed to react with oxidizing agent, this is oxidized into an alcohol due to this alpha hydrogen, which on heating loses carbon dioxide and acquires this structure on further heating. It is oxidized into a ketone which tautomerizes further on heating and further oxidation takes place to produce this tricarboxylic acid. And this tricarboxylic acid is called camphoronic acid. Camphoronic acid. Hence, the formation of camphoronic acid is due to the oxidation of camphoric acid. The structure of camphoric acid is finally confirmed by its synthesis. Finally confirmed by its synthesis. In which the starting material is diester of glutaric acid. The starting material is glutaric acid derivative dimethyl ethyl glutamate. When it is heated with strong base like sodium ethoxide, it will lose alpha hydrogen Then a condensation reaction is allowed with oxalic acid ester, We have then COOET, first condensation takes place and same reaction will take place Dickmann condensation. We have then on treatment with sodium amalgam, so before reducing this ketonic group, the first cyclic compound obtained due to this Dickmann condensation, we will methylate, monomethylate the alpha hydrogen. This ketonic group, these two ketonic groups are then reduced into alcoholic group by treatment with sodium amalgam. We will then have CH, OH, OH, CCS3, COOET, CH, COOET. These two groups are removed. First on treatment with conc HBr and then by zinc acetic acid treatment, reduction. It is first converted into bromo derivative and the bromine from saturated carbon is removed. Saturated carbon is removed by the reduction process. We have then CH2, CH2, C, CS3, alkaline hydrolysis, followed by acidification. We will finally get our required acid. That is camphoric acid. Hence, we have verified the structure of camphoric acid by its synthesis. As this camphoric acid is the oxidation product of camphor, which was bicyclic compound, saturated, and ketone on the ring carbon On the basis of these informations, we can imagine two structures for camphor. Number one, this one, or number two, this one. Because these two structures can produce camphoric acid. Camphoric acid. See here. If this is the structure of camphor, we have and if this is the structure of camphor, we have again camphoric acid. Imagine this is structure A and structure B for camphor. As structure A on iodine reduction is converted into carbachol, and this compound, this phenolic compound, is not obtained by the structure B. So we can finally conclude that the structure A is the actual structure of camphor. Camphor this is not formed. So we have reached near the structure of camphor. This structure A of camphor is finally confirmed by its synthesis, in which the starting material is camphoric acid. Synthesis. Starting material is camphoric acid. When heated with acetic anhydride, this camphoric acid is converted into camphoric anhydride, camphoric anhydride, this carbonyl unit of anhydride is crowded and it is less crowded. So when it is allowed to react with sodium amalgam, this carbonyl group is reduced due to less crowding, and we have this reduction product on treatment with KCN will generate on hydrolysis. This is converted into calcium salt when allowed to react with calcium hydroxide. This is converted into calcium salt and this calcium salt on heating gives us a ketone. this cyclic ketone, which is camphor. So we have now established the constitution of this camphor. Our camphor having two asymmetric carbons. So due to this reason, the compound must be optically active. And these two asymmetric carbons are different. So 4 optical isomers are expected. But in nature, only 2 optical isomers of the compound are available due to fusion of the ring. This is camphor. So we have finally established the structure of camphor, and this compound is very useful for us. Thank you.